Hello everyone, welcome to Andy's RISC-V webinar. With us today we have John Ming, Director of North America Field Application Engineering. Today, John will talk about RISC-V and SoC architecture exploration for AI and ML many-core compute arrays. Before I hand the mic over, I have a few housekeeping items to cover. Today's webinar will be available on demand after the live session on Andy's website and YouTube channel. The slides will also be available for download on the website. So without any further ado, I'd like to welcome our speaker today. John, over to you.
Okay, thank you, Rachel. Hi, good morning, those in North America, and good day to everyone else. We'll get started quickly. Today we'll talk about Andy's briefly. We'll talk about RISC-V as a review for all of us. And we'll talk about a couple of ways to implement microarchitecture, multi-core architectures, and some of the pitfalls and best practices. And I'll briefly introduce you to our custom extension vector processor and how we implement a high bandwidth, high compute multi-core engines. And we'll briefly touch on development tools. Okay, let's get going. Andy's is a pure play CPU IP company. We're an IP company, and that's what we specialize in. We're a founding member of RISC-V International. We're a public company, and we're a major contributor to open source, and we maintain many of the projects. We actively participate and run many of the task groups. So quick facts, we're about 15 years old with over 200 licensees worldwide. Over 80% of the company are R&D employees, and we have shipped over 5 billion accumulated SoCs with our technology. Andy's site is our custom development tools, and we have many seats and many engineers using them. We have offices around the world. We're headquartered in Taiwan, but we have offices, sales and R&D offices around the world. So we're a global company. So just quick overview of terminology and products. At the top, we have our own architecture called AndyStar V5, which incorporates RISC-V architectures plus Andy's specific performance extensions. Below that, we have processors called N series, which are more of a microcontroller, D series, which have DSP extensions, which are RISC-V P extensions enabled. A series cores that comes in single and multi-cores flavors are able to run high-level operating systems with their virtual memory support. Lastly, we have V series cores, which are a combination of ND and A series, which implement RISC-V vector extensions. So we have to go from very small microcontroller to running Linux to actually high-end vector engines. And where do we see customers using this, our Andy's V5 adoption? Well, we're seeing a lot of interest in AI, starting from ADAS, IoT devices, blockchain, microcontrollers, multimedia. And we are seeing a great adoption in data center AI accelerators, either as controllers or AI engines, in the storage devices, and particularly now 5G macro and small cells. We are seeing customers implement anywhere from 1 to 1,000 plus cores. So we have wide range of customer implementations. So quick overview of RISC-V vectors. RISC-V vectors was designed to mimic or designed to calculate many math operations, and it improves performance by arranging memory. So just like Cray-1 devices from 1970s, we are able to calculate the memory and the flexible register architecture. So kind of applications we are currently actively seeing for vector processors today are computational kernels, like matrix multiply, FFT sort, which are building blocks of a lot of higher algorithms. cryptography, machine learning, deep learning, particularly AR, VR applications. A lot of multimedia processing, networking, and scientific computing. So what's all common about all these tasks? A lot of these tasks are obviously mathematically heavy computing, but all of them can be and are multi-threaded. So they're all suitable for parallel processing. To exploit this, we want to look at what in real life applications, what that looks like. Well, there are single-threaded applications and multi-threaded applications, depending on the performance you're looking for. So let's look at a web browser. Used to be, in my earlier days, when web browsers first coming into computing and set-top boxes, it was a single-threaded application because it generally didn't need to be very fast. It was human interaction time. However, today, I opened up a web browser last week and looked at how many tasks it spawned off. For a single tab, one tab of Google Chrome took 16, it spawned off 16 tasks. On a contrast, PowerPoint, where I was making the slides, only spawned off one task, which was kind of interesting. So there are a lot of single-threaded applications, but then there are a lot more multi-threaded applications. The reason to do going multi-thread is break up independent tasks to accelerate performance. So let's look at the Chrome browser. Well, obviously, browser needs to get the data from the network. It has to render any images and fonts, and then it has to render the page on the screen. So it is truly multi-threaded. I could do it single thread. And what's the customer response? Or people looking at this web page might say, oh, either A, my computer is too slow, or B, my network's too slow if the pages are rendered sequentially. We've seen all those pictures where it starts from upper left and starts rendering down. If I do it multi-threaded, I could do those tasks simultaneously and gives a better experience. So now multi-threading or multi-cores have a true benefit. So how do we go about doing this? Well, you want to get the processor or engine that fits your single-threaded requirement. So basically, I could have a one big processor that could do single thread very fast. However, that still has a limitation of waiting. One task has to finish to move to another task. So what you want to do is when you go to multi-core, divide up the tasks and find the engine that could meet the requirements for the worst case tasks. For us, that might be configuring the CPU with different memory subsystems, different CPU features like vectors, our custom extensions, maybe bigger memories or bigger caches. So there's a lot of experimentation to be done. And once you find an engine, the easiest thing to do is start duplicating. You scale up to 2, you scale up to 4, 8, 10. So by having a basic engine, it's simple to implement, verify, then duplicate functions. However, eventually, the bottleneck happens, which is bus bandwidth. Let's say one CPU accessing one memory space, it gets 100% of the bandwidth. 2 CPUs, it gets 50%. And now the CPUs can only theoretically be only 50% efficient. You need the data and instructions to run it. So you start having bigger caches, bigger memories, but ultimately, eventually you do run out of space in that you do run out of memory bandwidth or bus bandwidth, device bandwidth. You just run out of bandwidth. Your engines are waiting more than running. So the other alternative is to solve this data delivery problem is bring the memories closer to the processor. There's a proximity of data. Some tasks are only going to be shared with other similarly configured engines. So use the proximity, use the data locality optimize that. And lastly, reduce bandwidth contention. So having local caches in the CPU is great. Secondary shared memory or the level 2 caches is also a good solution to reduce moving data unnecessarily. Lastly, you use those building blocks to optimize multi-core. So you have the single cores and you start designing clusters and duplicating those clusters. And it's much easier and reduces the risk. Verification effort is minimized. It's easier to debug. When you have a problem that's across thousands of cores, well, you could try to debug it by running it on the single core sequentially as well. So it's much simpler debug methodology. It's easier to program, especially I could migrate tasks from one cluster or one processor to another one. So it's a good configuration, good optimization. And by separating the buses as much as possible, you can have multiple memory controllers, multiple local memories. And idea is to minimize data movement, exploit the locality of data. So how do we extend CPU performance further? At the top, you see the typical pipeline of a processor. There's instruction fetch, decode, execute, and write back, and retire. With that, a lot of processor companies in the past have started adding extra execution units. You could go superscalar, or you could also go multiple execution units. So this example, this is a typical pipeline of our NX27B vector-enabled processor. We have a scalar CPU pipeline. However, scalar CPU pipeline, it moves the data, moves the instructions to our vector processing unit. And vector processing unit really is a superscalar, a multipath, almost out of order vector processor. So it uses a CPU to control the data, and vector processor in some ways very high level acts like an accelerator. So typical speed up we see using vectors versus a scalar processor. For fundamental mathematical functions and AI functions, we're seeing about 20 times speed up, which means a task that might take 20 minutes will take 1 minute using vectors. On the higher level functions, like 32-bit matrix multiplication, we're even seeing up to 60 times speed up. So it is a good engine, good accelerator to build into your basic processor. So, excuse me, how do we even extend the processing further? Well, we have something called Andes custom extensions. Right? When we think about custom extensions, everyone thinks about instructions, and that's what we do as well. Block diagram at the top, it shows the scalar processor again. At the bottom, we could start implementing our own custom instruction set. We have a tool that automates a lot of this process. We'll handle instruction decoding, partial decoding of the register data values, and then the execute control engine. So in the end, user only has to worry about custom specific processing, in fact, adding an ALU. But this still doesn't solve a problem of data movement. However, it does solve problems of performance efficiency. So by executing one instruction instead of many instructions, we reduce a lot of the bandwidth on the buses. Secondarily, there's a secondary effect by executing fewer instructions and reducing bus bandwidth, we actually save power. So there's a execution efficiency, you save time, and you even save power. Basically, it could work really fast and give you more chance to go to sleep or low power mode if that's your user mode. So basically, speed ups we see, typically we want to see at least 20, 30 times speed up. For CRC and triple DES operations, we actually see hundreds of times speed up. Basically, we gain we gain bandwidth. If we speed up 100 times, we're fetching probably 100 times less, executing 100 times less. So we save power, bandwidth, and efficiency as well. However, not only that, remember we talked about exploiting locality of data. Well, what if my custom instructions could have a private bus and have a private memories? So that's what we also support with a custom extension, not just custom instructions, also allowing private memories or even shared memory space that multiple processors could share the memory, work collaboratively, and reduce bandwidth on the main bus. So now we're sort of splitting perhaps scalar operations from the custom operations, and these could be matched to the vector operations as well. These memories can be used by vector unit as well. So there's a lot of different configurations, optimization options to get data into the processor, operate, and getting data out and sharing with other processors. So here's what some implementation might look like. So on the right, we might have a system periphery bus. On the left, we might have a control bus. And then the processors will have the caches, local memories, bus interface unit. And then using custom extensions, we could create an arbitrated memory space, local memory space, with the perhaps priority. When core 0 is doing a sort of high priority task, core 1 is assisting. We could say memory access should go to core 0 first. Core 1 can start or operate out of the local memory. So this kind of picture draws a lot of DMA, data movement, loads and store movement. And one option you can do, and other customers have implemented, is you could do a custom load store operation that loads and stores multiple memory locations or registers. So a lot of options are available to optimize CPU architecture, data movement, and also the local memory space. So what other things possible is to add the control ports, custom ports. So now when my processor doesn't have enough horsepower, okay, then we could control multiple external accelerators. This might be typical in a sort of graphics engine or AR, VR type of applications, where you want to have a dedicated path or a processor, because custom accelerator could be a processor. The main processor controls the control flow, and then the accelerators do the data flow. The CPU have a wide data bus to control and access external peripherals, and then the memories. So we're putting together big engines. How do we ultimately use it? We're a processor, so we're all CPU software dependent. So we have a standard tool called AndySite, IDE. It includes the compiler, debugger, and then the simulator, and then basic computational libraries to develop software effectively. Our simulator and the development tools support multi-core programming. So it's a one-stop shop. However, you can use third-party tools as well, third-party simulators, third-party compilers and debuggers, including open source ones. Advanced tools-wise, we're supporting AI compiler through LLVM, and we have special tools, advanced tools, like Andy's Clarity. It's a pipeline visualizer and analyzer. So DSP programming is a little different than control programming, where DSP, data movement, and pipeline bubbles are very important. So we have a tool that could view a pipeline view of instruction flow and usage of the functional blocks. And we could see the resources, and most importantly, we could see the stalls and bubbles very easily. Here's a picture of our Clarity tool looking at pipeline. This vector unit, you could tell immediately. You could see that there are 4 vector adds floating point math happening simultaneously, and those are highlighted in boxes. And we could see where the instructions flow, what the bubbles are, so that I could optimize the program at assembly level if I wanted to. And this helps me to play as a programmer or architect to decide where to place loads and store operations, and most importantly, whether I need a different loads and store engine, more bandwidth, less bandwidth. Is my CPU starving, or spending more time waiting than processing? So, as a quick summary, we went over a lot of the topics at a high level. In the future, we'll get into more detail. But the flexible CPU architecture and flexible SoC architecture allows optimal multi-core implementations. However, performance optimization is critical to effectively process all these tasks. By having 1,000 cores, you want them as optimization as possible, utilize them highest as possible. Then power savings, you need to save power by exploiting locality and using ACE. When we say power savings, it's really data movement. It's no longer a compute that takes a lot of power. With the multi-core, data movement on the bus utilization actually uses a lot more power. Our custom extensions provide efficient data movement possibilities and expansion of the buses. Our standard buses we're now seeing going to 64 bits, 120 bits, and 256 bits wide bus movements. Well, those are important to feed all the data. However, as we saw, if we start adding a private local bus, they could even share memory. It does help reduce pressure on the main bus. And private bus, it could be optimized to that specific tasks. And then finding advanced software tools like Andy's Clarity for performance optimization is going to be more and more important, so that you can use those 1,000 processors very effectively. If I'm using 500 processor, 100% efficient, that might provide better performance than 1,000 processors that are 50% efficient. So there's a good optimal balance of number of processors, bandwidth, and the performance. And this technology will continue to be a partner and innovate processor IP. Basically, we'll innovate in terms of performance of the scalar unit. We'll keep adding vector unit. We'll keep enhancing our custom extension interface, mainly the CPU interfaces, so that you can end up with a most optimal compute engine possible. Okay, thank you for listening. If you have any questions, I'll be glad to entertain them.
Thank you, John. So now it's time for us to take questions. So if you have any questions for our speaker, please leave your questions in the chat box. Okay, the first question we got is, does Andy's plan to support vector extension on cores with higher performance in the future?
Yes, we are actively working on the two fronts, the higher performance processors. And also, we're looking at the vector specification as it grows in hardware, and also in terms of providing more software libraries to optimally use those processors.
All right. The second question here is, could you elaborate a bit more on how ACE increases performance efficiency in terms of RISC-V compliance?
Okay, so RISC-V architecture allows custom extensions. So the RISC-V architecture itself allows customers and CPU IP companies to provide these custom extensions. They're not part of, as any specific extension is not part of RISC-V standard. However, you can be compliant by deciding whether you want your custom instructions to be to be RISC-V compliant by whether it could be replayable, or you could do a custom instruction that's always executes, assumed to be executing independent of whether the CPU takes an interrupt or not. So there are a lot of ways to decide how much compliance to RISC-V standard architecture you need. It's ultimately in-user decision. Having custom instructions itself, custom extensions, is part of RISC-V architecture.
Okay, I think we covered all the questions today. So thank you, John, and thank all of you joining us today. Today's recording and deck will be available on Andy's website, and Andy's will hold more webinars in the future, so stay tuned. See you next time. Bye, John, and bye, everybody.
Bye.
Bye.